Hi. In our last videos, we finished with limits theorem, and then we moved to continuity of a function. Okay, and look, now we're going to move to the new subject, differentiability of the function. So our ability to find derivative of the function. But look, now that we moved away from limits, we're still going to use the theorems we've explained before. We can now move to old notations with functions because this is the one we prefer. And look, continuity condition can be written as the limit with x approaching some x0 out of f of x is equal to f of x0. So again, limit of a function at some point must be equal to the value of the function. Now, differentiability condition can be taken directly from the definition of derivative. So look, derivative of a function at some point x0 is given as limit with delta x approaching 0 out of the difference quotient delta y over delta x, which is in notation more familiar to us, equal to limit with delta x approaching 0 out of f of x0 plus delta x minus f of x0 over delta x. And look, the condition for differentiability is very simple. This limit must exist. So if this limit exists, this means we can calculate a derivative. And look, because we're going to be very soon proving a lot of differentiation rules, let me introduce a notation that will actually make all our jobs easy. Okay. Let me draw it like any function. Well, this function is usually called logistics function, but we will get to it at some different point. And what we have over here is the initial value of x, so x0. Now, we were stating that x is changing, let me write this nicer, by some amount, delta x, and we are ending up at a new point, x0 plus delta x. And look, for those 2 points, on the function, we can calculate the value of the function. Here, it was f of x0, and here, very unpleasant f of x0 plus delta x. So look, what I'm going to do now is that I'm going to introduce new, simpler notation. Let's just say that this point we will call n, this point we will call x. So consequently, here we have f of n, and here we've got f of x, which makes things simpler already. Okay. Now, when we calculate derivative, right, we want delta x to go to 0. So this distance should be getting smaller and smaller and smaller. So look, in the old notation, we were writing that delta x going for 0. But look, what will we see happening if delta x is going for 0 in mu notation? We will see that our x is getting closer and closer to n. So, in other words, we can replace this symbol with x approaching n. Well, and this actually makes our job easier right away. Why? Look, now continuity condition. Okay, let's denote continuity condition with a red color. Can be written as f limit with x with x approaching n, right? Instead of x approaching some value x0, out of f of x is equal to f of n. Okay, so look, now differentiability condition, this one, which was far more problematic, is given by, and let's denote this by green color. Now, look, we will have the limit with delta x approaching 0. So, again, x approaching n out of f of x minus f of n over delta x is equal to x minus n. And this is going to be equal to our derivative f prime of n, not at x0, because x0 is replaced by n. Okay, so now let's make some connection between differentiability condition and the continuity condition. Okay, so how do we do that? Okay. So first, let me write just that f of x minus f of n is equal to f of x minus f of n. Well, I hope nobody is going to disagree that this is true. Both sides of the equation are exactly the same. And look, I'm going to do a very simple thing. I'm going to multiply both hands, this side of the equation by 1, which is permitted, right? Nothing should change. But my one is going to look a little bit different. My one is going to look like this. This stays the same, but here I'm multiplying by x minus n, dividing by x minus n. And I'm multiplying by x minus n. Because those two cancel each other out, we still have 1. Okay, let's denote, those are the colors I've got. Let's denote this side, left side, which is very true, and this side, right side, which is also very true. Okay, so look, I'm going to start with the left side. And what I'm going to do in the left side is I'm going to take a limit with x approaching n out of this f of x minus f of n. Now, can we do something with it? Well, I think we can. Why? Well, because we know some rules on how to deal with limits now, right? And we know that this is simply limit with x approaching n out of f of x minus limit with x approaching n out of f of n. But look, over here, if we've got f of n, it means we are already at point n, so we can simply rewrite this as limit with x approaching n out of f of x minus f of n. Okay, I think you cannot see this color, so I'm going to replace this one with L over here. This is our left-hand side. Okay. Now, let's go to the right side and let's do exactly the same thing. So, let's take what we have on the right hand side, and we know they are equal to one another, and let's calculate the limit. So here I would calculate limit with x approaching n out of very big expression f of x minus f of n over x minus n times x minus n. Right? And again, I can use the rules on limits, and we know that the product of the limit is a limit of the product, so I can divide this into two separate expressions. So here we have limit with x approaching n out of f of x minus f of n over x minus n times limit with x approaching n out of x minus n. Okay, so look, what do we have? Over here? Look, I hope that you can even notice, just by looking at the blackboard, that this expression over here, we've already seen something. And of course we did. This is nothing more than a definition of the derivative that we have over here. So I can simply replace this with f prime of n, right? So I get that this is f prime of n. Now, look, as x is approaching n, then we get over here n can replace x. And what do we get? Here we get derivative, but then we get just 0, right? This whole thing is equal to 0. So we get that the right-hand side of our equation is identically equal to 0. Okay, so what can I do next? Well, let's equalize again left hand and right hand side after we went through all the struggle of rewriting them in a different form. Okay, so left hand side is blue and it's equal to right hand side, right? So what did we get? We get that limit with x approaching n out of f of x minus f of n is equal to 0. But from this, I can get a limit with x approaching n out of f of x equals f of n. Now, where did we see this result? This result is nothing more than the continuity condition that we see over here. Okay, so let's summarize all the steps we have taken. We got that if I take a limit of the left-hand side, I'm getting this expression. Now, if I'm taking a limit of the right-hand side, I'm getting 0. But for us to get 0, first we must be able to find the limit. Right? Because what if there's no limit? There's infinity, or there is negative infinity. A lot of problems. So look what we get over here. For us to be able to establish this result, which is continuity condition, we needed to have differentiability condition fulfilled. So what we get out of this is that differentiability implies continuity. In other words, if we can differentiate a function, we can be sure that the function is continuous. But remember, it doesn't work in the opposite direction. If we have continuity, it doesn't imply differentiability. Okay, now if I'm saying that, maybe I should show you an example of a function that is continuous, but is not differentiable. So we cannot find a derivative of this function. And we already discussed this function a couple of videos ago. Okay, so let's just say that our function y equals f of x is given by x minus 2 absolute value plus 1. Okay, look, it's really easy to draw this function. We would start with absolute value of x, right? Which would be, okay, let me show you the transformations. So this would be y equals x, then y equals, for example now, y equals absolute value of x would be, this part stays the same because it's positive, and what used to be negative becomes positive. So this is y equals absolute value of x. Then we need to move this function by 2 to the left, right? And by 1 up. So as a result, we are obtaining a function that looks like this. And here we have 2, here we have 1. Yeah. Okay. Now, is this function continuous? We need to, well, of course it's continuous, right? Why do I know? How do I know this? Look, if I'm drawing this function, I'm doing it without picking up the chalk. Okay, but as it turns out, this function, even though it's continuous, it's not differential. We cannot find derivative of this function at one very unpleasant point. And which one? Well, I hope you can find it and you can guess it right away. Of course, at this point. Right? Look, at this point happens something new that we haven't considered before. Look, when you have a polynomial function, it's smooth, right? We can find derivative everywhere because this function is smooth. What appears over here is this sharp edge. And this sharp edge creates a confusion that is not allowing us to find the derivative. Okay, so how can I show that I cannot find derivative for this function? Look, what we are doing now is we are showing counter example. So we are showing one example that can break the entire rule. And look, in our case, what we need to do is to show that limit with x approaching 2 out of the expression f of x minus f of n over x minus n does not exist. Okay, so what will we have over here? Here we're going to have f of x minus f of n over x minus n. And now let's substitute. What is going to be our n? Well, our n is going to be, well, 2, right? That is the point at which we are going to prove that something wrong is happening. Okay, so we will have f of x minus f of 2 over x minus 2. Okay, now knowing this, we can easily start substituting for for f of x and f of 2. Okay, so what am I getting over here? Well, I need to still write limit with x approaching 2. And now, f of x is this function that we have over here, right? X minus 2 plus 1. Now, f of 2 is the outcome of putting 2 instead of x. If I put 2 instead of x, I'm getting 0, right? So I'm left with just plus 1, but I have minus up front, so it's minus 1 over x minus 2. So look, what am I getting over here is limit with x approaching 2 out of x minus 2 over x minus 2. Okay, but when we look at this, first look says, but this is gonna be 1. Well, not necessarily. In this case, a good thing to do is to actually calculate left side limit and right side limit separate. And let's break with tradition today. And okay, let's not break. Okay, give me a second. Okay. Give me a second. And now, let's break with tradition today. And let's start with right side limit. Okay, so we've got limit with x approaching 2 from the right side. Okay, now let's figure out what is happening over here. Look, if x is approaching 2, but this expression that we've got over here, is showing us that we are approaching 2 from the right side, which means from values higher than 2. What does it imply for the absolute value inside? Well, I would say that this implies that actually x must be bigger than 2, right? Because it's going to be bigger by 2, or bigger from 2 by just this tiny amount, but it's going to be bigger. And look, absolute value of x is equal to x if x is bigger than 0, right? So how can I rewrite this expression? I can rewrite it as limit with x approaching 2 from the right hand side out of x minus 2 over x minus 2. This is the limit with x approaching 2 out of 1. This is 1. This must be 1, right? And this is exactly what we said before. This is 1. Makes sense. Okay. Now, let's see what happens if we calculate the limit from the left-hand side. Okay, look, now when I'm substituting here a number, I'm substituting a number like 1.99. So this is a number that is smaller than 2. So if I subtract 2 from it, I will get a negative number. And absolute value of x is equal to negative x if x is lower than 0. So, what should I do? If I want to get rid of the absolute value, I should change the signs of everything inside. So what am I getting over here is basically minus, the limit with x approaching 2 from left-hand side out of minus x minus 2 over x minus 2, right? Those two cancel each other out again, but then I'm getting that this is a limit with x approaching 2 from left-hand side out of negative 1. Limit of a constant is a constant. It is negative 1. So, what do we see from this? The right-hand side limit out of f of x minus f of n over x minus n is different than limit, the left-hand side limit out of f of x minus f of n over x minus n. And if this is the case, this means that the limit does not exist. Okay, what did we learn from this example? Look, generally, functions that we can differentiate are continuous functions, with one tiny exemption. They cannot have sharp edges. We can differentiate functions that look like this, but we cannot functions that look like this. And of course, look, let me be precise. We can still differentiate this function here and here, and here, and here, and here. Those are everywhere places where I can find derivative. The problem is this point and this point, this point, and this point, and this point again. Look, so we cannot find derivatives at sharp edges. As long as our functions are smooth, we can differentiate them as much as we can. Okay, so this is it about differentiability and continuity of a function. Since the next video, we're going to start introducing differentiation rules. Okay, take care.